Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 32. Now, by the end of last class, we had seen that lambda equals h over p. Lambda equals h over p, or this is what we had seen in the last class, right? I had stopped with the derivation of this particular equation. I should be more careful and precise. We didn't stop with the derivation. We stopped with how Planck came up with this expression. Okay, so Planck proposed this expression where h is the Planck's constant and p is some momentum variable and lambda is some momentum variable. Okay, now from this equation, if you were to recall from the last class, how did we get this? Just to give a brief recap, we obtained this from E equals h nu, which is hc by lambda. And by recognizing that h by lambda has dimensions of momentum, and also that based on classical electrodynamics, starting from Maxwell's equation, you can show that your E equals Pc, therefore. E equals Pc. We did not rigorously derive this. Okay, please notice, we did not rigorously derive it, neither did de Broglie. All right. Now, what is the objective of using this particular equation? Recall from the previous two lectures that waves and particles are completely different entities. Okay, right? When waves and particles are different entities, the wave-like nature of something and its particle-like nature, right, had to be interrelated. Why was this? Because of the phenomenon of duality. Okay, right? So waves and particles are two completely different entities, but light, it was shown by the black body expression and Planck's explanation of the expression E equals nh nu. To these two ideas, we came to understand that light was both a wave and a particle, where wave and particles are completely different entities. I also told you yesterday that matter, that is, electrons, atoms, molecules, and even some big molecules, right? They also exhibit wave-particle duality. But how to quantify or how to connect a wave-like nature of a wave particle with its particle-like nature? For that purpose, the de Broglie equation is very helpful. Okay, right? This is a de Broglie relation. And this lambda is what is called as the de Broglie wavelength. All right. And this momentum is the momentum of a wave particle. Now, this is a standard expression you have been using since your 11th standard. No big deal about it. But its implications are important. What this equation tells us is that, greater the lambda, that is, higher the de Broglie wavelength, the more greater lambda implies wave-like nature predominates. And larger P implies particle-like nature dominates. All right. This is because, the mass is going to be a contributing factor for the larger momentum. And the proportionality constant, it turns out, is h. All right. So using this idea, lambda equals h by p, de Broglie could actually connect and quantify the wave-like nature of something with the particle-like nature of something. All right. So just to be on the same page in this course, recollect that we were discussing about detecting molecules in space. As part of detecting molecules in space, we had to understand the nature of how light interacts with matter, right? And light, we discussed, was both a wave and a particle, with our understanding that waves and particles are two completely different entities, and in different experiments, light exhibits different types of properties. For example, in some experiments, such as when it undergoes diffraction and all, it exhibits a wave-like nature. Whereas in other experiments, such as in black body radiation and in photoelectric effect, it exhibits particle-like nature. Overall, it has dual character. Similarly, matter, that is electrons, atoms, molecules, etc., they also exhibit a wave-particle duality. We didn't go through the details of why matter would exhibit wave-particle duality, but through a series of experiments, matter is also known to exhibit wave-particle duality. All right. And to quantify this wave-particle duality, we have this expression, de Broglie relationship. Okay, right? So now with this idea, in fact, we can always solve a few problems using the de Broglie relationship. That we shall keep aside for the tutorial sessions and see how it is particularly useful in the context of astrochemistry itself. Okay, but that besides, so we have now seen that matter, right, especially at the microscopic level, we're talking about dimensions approximately of the order of 10 to the power minus 10 meters, or even up to like say something like 10 to the power minus 8 meters, right, exhibits wave particle duality. All right, so matter does exhibit wave particle duality. Now the fundamental idea is that because of this wave particle duality, one cannot use the conventional equations of motion, such as, for example, your classical equations of motion developed by Newton to describe the motion of these particles, of these wave particles, or these microscopic entities in this dimensional scale. We're talking about a lot of molecules, atoms, electrons, etc., etc. Are we clear? Okay, right? So the key point to emerge from this wave particle duality is that the motion of the wave particles, right, can neither be described fully using wave equations or equations of motion in classical physics. All effectively starting from F equals ma, right? So you can neither use the wave equations, your conventional wave equations, nor can you be using your equations of motion based on classical physics, because it's neither a wave nor a particle. All right. In fact, these particles, right, which exhibit both wave and particle nature, right, these wave particles are what are called as quantum mechanical systems. And the matter, the matter with which light interacts in astrochemistry, right, they're all quantum mechanical systems. And so the matter in astrochemistry with which light interacts they're all quantum mechanical systems. Is this point clear? So therefore, the matter that we describe in astrochemistry is not purely classical mechanics. It does not correspond to a picture of classical mechanics, but rather it obeys the laws of quantum mechanics. And what do I mean by quantum mechanics for our purpose? These are systems which exhibit wave-particle duality. All right. Are we good with this understanding? Now, what is the key idea to emerge from the ongoing discussion? The ongoing discussion is that the molecules and the various atoms that light interacts with in astrochemistry. That is, for example, the potassium atom, the hydrogen atom from sun, or the CN radical, the CH plus radical, the CH plus species, which were detected, or the ammonia molecule, which was detected in the ISM, which we discussed earlier, right? Their equations of motion cannot be described simply by using F equals ma, right? But rather, quantum mechanics has to be used to describe their motion. So to further understand, right? To further understand how exactly light interacts with matter, right? In the context of astrochemistry, we need to understand some fundamentals of quantum mechanics. Just some fundamentals. We need not go deep into quantum mechanics because that will be a new course of its own, right? In fact, there are different flavors of quantum mechanics. There is going to be a time-dependent version, there's a time-independent version, and the application of each of these versions depends on the context. For example, what kind of systems are we applying the quantum mechanics to, etc., etc. In the context of astrochemistry, we need not go to the greatest of depths as to what is going to be the precise type of equation used. However, it is good to know that some basics of quantum mechanics is used to understand the matter that is relevant in astrochemistry. Is this point clear? On that note, our next idea is going to be to study, some fundamental properties of these quantum mechanical systems, right? As relevant to astrochemistry. Recall, see, notice where we are, okay? We started off our discussion with molecules detected in space and how we are going to detect them, okay, right? But as part of how we detect them, right, so much of the fundamental science, for example, we had to understand how molecules rotate, vibrate, etc. at a very elementary level. And this was followed by the discussion of the electronic states. And this was followed by, an understanding of what light itself was, and why it can't be simply described as a mere wave or a particle, and that duality is involved there. And not just with light, but also with the matter with which light interacts, that also exhibits dual nature, right? And these wave particles are also called as quantum mechanical systems, and the equations used to describe their motion are not the same laws of equation, such as like classical physics, that is F equals ma, because we're neither talking about waves for which the wave equations, the conventional y equals a sine omega t plus kx, a sine of omega t plus kx, those type of equations, right? They will not be satisfactory, and even purely classical physics type equations will also not be satisfactory. So how do we actually incorporate both wave nature and particle nature to these quantum mechanical systems? This is what we shall be seeing in the next section, and we shall, once we see how this is done, right, I shall be discussing its relevance in the context of astrochemistry itself. All right, yeah, right. So the task now is to describe the motion of quantum mechanical systems, right? So we have to describe the motion of quantum mechanical systems with the knowledge that we have to include both a wave nature and a particle nature. We have to include both a wave nature and a particle nature in this equation. All right. So where do we start with? We start with starting point is going to be what is called as a one-dimensional wave equation. Let's simply consider an equation of this type. Now, this is the wave equation for a wave traveling in one dimension. When I say one dimension, it's along, let's say, u is the dependent variable, right? And x is the independent variable. So u, as it travels along your x direction, that is what is called as a one-dimensional wave. We'll start off with this simple equation, okay? Now, how do we get this equation itself? This is the standard wave equation, right? Now, this can also be derived. By assuming, by simply, balancing out the various forces at any given point on the wave, okay? We might, look into how this equation is derived in the tutorial. But for our purpose, let us start with this point, all right? we're going to start with this point, and we're going to start off with the wave equation, and we shall see how we incorporate particle type nature to this wave to make it a wave particle, right? How we know like this wave particle equation is going to be used in astrochemistry. All right. So please don't lose sight of the bigger picture as we get involved in these details. This is an astrochemistry course, okay, right? And we're doing all this to understand, to see how molecules are detected in space, and also to understand the behavior of molecules in space as we can perceive from here. Okay, that's it. All right. And as part of this venture, that is, to apply such equations in astrochemistry, recall what all areas we have covered. In the first few phases, right? We were discussing from the chemical aspect, the chemistry aspects, the various chemical equations involved, the various structures of the molecules involved. So that was the chemistry aspect. Later on, we started off with some classical physics aspects. We started off with some spectroscopy aspects. What happens when an atom gets excited, right? The different types of motion, the classical thermodynamics was involved. And now we are venturing out into an area called as quantum mechanics. Now, these many interdisciplinary areas are actually required to completely understand astrochemistry, okay, right? Because astrochemistry is a highly interdisciplinary and applied areas, a fundamental knowledge involving very many areas are essential. So that's why, we started off with chemistry, and then we traversed through some aspects of physics, such as like thermodynamics, etc., and we have now landed up in quantum mechanics. And we shall very soon see how this quantum mechanics is applicable to astrochemistry itself. Okay, so we're going to start with the wave equation. Now, every time I give you an equation, what is the first thing to do? As good physical chemistry or chemical physics or like astrochemistry students, the very first task to do, like once I've given you an equation, is to check for its units and dimensions, whether the units and dimensions on the LHS and the RHS are going to be matching or not. Okay, in this case, okay, right? In this case, now, what is the denominator here? It's dou square of x square, right? So this is going to be of what magnitude? And what about this folks right here? And what is v here? V alone I'll give you, okay, right? V is nothing but nu lambda. This is v, this is nu, okay, right? This is v and this is nu. And so v is nu lambda, which is nothing but wave velocity. Right? So what is going to be the dimension of velocity? Well, the velocity is going to be meter per second ms to the power minus 1, right? Meter per second, right? So velocity square. So v square is going to be v to the power minus 2 is going to be m to the power minus 2 and s square. Okay, that is this folk. What about t square here in the RHS? Well, t to the power minus 2 is of course going to be per second the whole square, okay, right? Are we clear? So the RHS, right? And what about this u which is a function of both x and t? What about its unit right here? What are going to be the units of u here? Well, we'll look into the tutorial, okay? For now, take it that u has no units. Okay, right? I'll give it to you as a homework to figure out why u has no units. Okay, we'll also look at it in the tutorial also. All right, yeah. So therefore, the net dimensions in the RHS is going to be t to the power minus 2 times v to the power minus 2. This is going to be meter to the power minus 2, correct? Right? This is going to be the dimensions on your RHS. What about the LHS? Again, knowing that u has no units, this is like x to the power minus 2, which is going to be m to the power minus 2, which matches the unit of RHS with the LHS. So therefore, we are dimensionally good. And note though there is still one caveat. I haven't explained why u still has no unit. Okay, we will look into that in the tutorial. All right. So we start off with this equation. And having completed the dimensional analysis, Now I'll delete this part. Okay, now see this equation again, this equation in page 4 right here, right? Now this is a partial differential equation. Now what is a partial differential equation? A partial differential equation of the second order. That is to say, second derivatives are involved here. Okay, right? And we must solve this equation. We must solve this equation. This equation, what is the variable we are solving for? We're solving for this particular thing, u of x comma t, right? Now, u of x comma t contains two variables, x and t. That is, it propagates through space along some direction arbitrarily defined as the x direction, right? And it also propagates with time. So we need to find this function u as a function of x and t, and this is a partial differential equation. Okay, right? Now, the standard way to solve any partial differential equation is that you have to first assume that the two different variables, that is, your x and t, they are separable. Okay, right? Now, to solve any PDE, by PDE I mean a partial differential equation, right? One needs to first assume the variables could be separated. All right. So we have to assume first that the variables could be separated. In other words, the function u of x comma t, which is a function of both x and t, right? That could be written as a product form in the form f of x times, say, something like g of t. All right. We make this assumption. Notice this. We don't know. This is not assure, but this is assume. Okay. Right. So notice that we have to first assume, in order to be able to find any solution to any partial differential equation, we must first assume that the variables are separated. Why is that? Well, I won't go to great detail, but I will just explain just by, looking at this equation. Okay. Let's say that, the wave function, let's say that the function here of x comma t, let's say that it cannot be separated. Okay. If it cannot be separated, then, as you partially differentiate this with respect to any one of them, there is always going to be a residual term. There will be a residual term compressing of the other variable, right? Which means that you will never be able to solve this equation. But once you make this beautiful product assumption that, I can express my u of x comma t as a separate function, as a separate spatial function containing only the x variable, and something as a function of t which contains the time variable. If I can make this assumption, okay, right, then I can solve this equation much easily. Okay. Now, having made this equation, the next step would actually be to substitute this particular separation of variable thing back in the equation. Now let's do that. So u of x comma t is given by this. So my dou u x comma t, with differentiating this with respect to, let's say, I want to calculate, I'll work on the LHS first, my dou x first. Okay, right? I differentiate this with respect to x, keeping t a constant. If I keep t a constant, my g of t is already going to be coming out, right? My g of t is a constant, so it is just some constant outside, and this is going to be some df of x by dx. Notice the point. The minute, I make this separation, the partial differential equations, where the symbol dou was used, has become d here. Why is it that? Because the minute I say dou, right, I have to indicate that, hey, I'm keeping something a constant, some other variable, which I don't know how to deal with. I'm keeping that a constant. That's what is happening in the partial differential term. But the minute, I take it out and keep it, it's already understood to be a constant, I use the notations d. It then becomes an ordinary differential equation, right? So now I have this. If I'm going to be, differentiating it again, right? If I'm going to be differentiating it again with respect to x again, right? Now what's going to be happening? This is already a constant. So this is outside. So this is simply going to be a constant as such. This will be untouched. and this will just be dou 2 f of x by dou x2. Are we good? So we've obtained the LHS to be this. Okay, this is the LHS of this term. If we now consider the RHS, which is, let's get to the RHS. So we've obtained the derivative with respect to the x, okay, right? The second derivative. Let's do with respect to t now. Now, dou u x comma t over dou t, okay, right? Dou t is going to be, once again, I'm keeping x a constant here. So this is going to be f of x dg of t by dt, right? And if I take the second derivative, this is already outside. So this is going to be d2g by dt2. All right. Are we all good? Now, having done this, okay, I'm now going to, make one more assumption. Okay. Assume, okay, right? Assume that my g of t is something of the form cos omega t. Now you may ask me, what is the validity of this assumption? In the first place, right? In the first place, when I made this particular assumption, when I made the assumption that the variables have to be separated, that was out of desperation. That was the only way, I could solve this equation. But now, having obtained these two expressions, you may now ask me, why do I need to unnecessarily, assume that my g of t is cos omega t? And where omega, what is omega? Omega is nothing but, what is omega? It's my angular velocity, okay, right? It's my angular velocity, which I'm going to be defining as 2 pi nu. All right, 2 pi times my nu, which is your frequency, okay, right? So my omega is going to be defined this way, as my angular velocity. All right, angular velocity. So what is the validity of this assumption? Can somebody please tell me? Why is it valid that I can assume that my g of t is cos omega t? Well, I'll give you an intuitive answer here. Okay, I'll give you an intuitive answer. The finer details will be actually looked into the tutorials. Okay, but for the intuitive answer here is that, hey, what is this equation after all? This is the equation of a wave, right? Now, when this is the equation of a wave, correct? Now, we know that waves are oscillatory. Waves are oscillatory. So, therefore, the equation of this wave, because it's oscillatory and it's going to be more or less symmetric as well, okay, right? Now, if it is going to be symmetric, the oscillations are best described either by sine or cosine functions, all right? Now, it doesn't really matter whether I choose cosine functions or sine functions, okay, right? Because I can express any cosine function as a sine function also, right? Because of the relationship, between sine and cosine. Sine of 90 minus theta is equal to cos theta, or like cos of, therefore, right? So this function can be expressed as a sine function also, right? Ideally speaking, I should have a combination of both sines and cosines, but a simplified version can always be this cosine omega t, okay, right? And so therefore, the basis for this assumption is that the wave is oscillatory in nature and best described by sines and cosines, right? Well, recall actually what is the equation of a wave that you have studied in school? It is y equals a sine omega t or like a cos omega t, correct? Where a is the amplitude. We can of course include some constant factors as well, but all of them will eventually get cancelled also. So therefore, I can get away by using this particular assumption itself. Okay, so I'm going to make this assumption that my g of t is cos omega t. The logic is that this wave is oscillatory in nature and it is best described by sines and cosines. Also because I'm kind of equating second derivatives, right? So I want a function whose second derivative gives me the same function. What kind of functions are there which satisfy? Well, sines and cosines definitely do that, right? Okay, so on that basis, I stop here. I stop this lecture with this particular point. So we have to describe the motion of the wave particles. For that, we started off with the wave equation, right? And we are trying to solve this equation by making some assumptions. That is, the variables could be separated, and after that, because of the oscillatory nature, and that somehow the second derivatives are being equated, right? I use for the time part some cosine omega t, where omega is the angular velocity. All right. On that note, I will meet you all in the next lecture. Thank you so much.